Hello everyone, my name is Yin Liu. Today I would like to talk about my paper, Privacy Preserving Sharing of Mobile Sensor Data. This work has been done at Virginia Tech during my PhD. Now I have graduated and joined Beijing University of Technology. Okay, now let's start. Well, I guess everybody uses a smartphone in our daily life. I feel like we cannot get rid of it. Well, also, we do not only use our phones to call someone or take pictures. Actually, we use a large amount of apps and their services. To personalize their mobile service, mobile apps continuously collect our data. It is obvious in order to have a good performance, mobile apps want the collected dataset get larger and larger and larger. To get there, how should they do? Maybe the most straightforward way is to do data sharing. Basically, mobile apps have three ways to share data. First, upload the data to the cloud and share it with other apps. And second, directly send the data to a destination app. And third, put the data to an on-device combined dataset. Well, we know that sharing is not always easy. It's not always happy and peaceful. Sometimes it is very hard. Let's look at some problems. For uploading data to cloud, there are four risks. First, cyber attackers can steal uploaded data by exploiting cloud servers' vulnerabilities. And second, insiders or careless employees can expose private data to the public. And third, governments can legally force IT companies to reveal their cloud stored data. And finally, there are several network connectivity and congestion issues. If you don't use cloud and want to directly share the data on device, there is also a problem. The receiver app can be leaking the received data unwittingly or intentionally. Well, apps can put their data to a trusted combined dataset, and this dataset will not reveal the raw data, but can be queried to get some valuable result. But these queries can be exploited to leak the data. For example, if we know the dataset contains only 0 and 1, then we can ask how many 0 are there in the combined dataset, and then we can ask how many 1 are there. Finally, we can reconstruct the dataset. So it seems that there is very difficult to protect data privacy when sharing the data. And that's why we need differential privacy. Differential privacy can really help in this scenario. I don't want to go deep into it and bore you with some complicated math formula. Simply, differential privacy is like, for example, we ask a question about the data, and normally we will get a result. But by applying differential privacy, instead of getting an actual result, we get a noised result. I mean, a noise will be calculated and added to the actual value. In that case, the actual value or real value is protected. Because the noise is calculated statically, the noise data can still reveal the property of the dataset. In other words, the noised data is still useful. So based on differential privacy, we provide our solution. We call it GoBetween. It is an on-device data sharing framework, serving as a trusted intermediary that aggregates the sensor data contributed by the collaborating apps, which execute expressive statistical queries against the combined dataset. The most important thing is GoBetween adds adaptively customized Laplace noise to the query result, thus properly preserving app providers' data privacy. GoBetween has four-phase process. First, Apps specify their privacy and utility requirements and transfer their sensor data to GoBetween. And second, upon each data deposit, GoBetween starts computing the noise scale for each built-in query operation. And third, collaborating apps black box query the combined dataset to infer the user's profile. And finally, GoBetween pass the query result with a suitable amount of noise, determined by the pre-compute noise scale, and return them. It sounds like straightforward, right? But actually, to apply differential privacy to our problem domain, there are several challenges. First of all, it is impossible to assign a fixed privacy level to all collaborators because app providers may have dissimilar privacy and utility requirements. And second, some app providers can infer user data from the combined dataset, contributing only minimal data. Basically, it only contributes some small dataset and want to get a lot of benefit from the combined dataset. And third, attackers can illicitly access or tamper with differential privacy operations and data. Our solution can overcome these challenges. First, we provide the privacy utility trade-offs that satisfy given privacy utility requirements. And second, we incentivize app providers to keep contributing data. And third, we secure the execution of statistical queries functions by placing them in a trusted execution environment, or TE for short, whose trusted storage persists the shared data collections. Let's first look at our privacy and utility trade-offs. Like I said before, our solution balances privacy and utility. For privacy, we have the formula to calculate the lower bound of the Laplace noise. So this is the formula. Rho is the probability that the adversary can correctly guess the absence or presence of a record in the combined dataset. N is the number of records, and delta V is the maximal difference between the query result of each possible combination of the neighboring dataset. It is a little bit complex, and I don't want to dig into it too much. Simply, if the query and dataset are fixed, then delta V is a fixed value. So basically, N is fixed and delta V is fixed. That means that we can tune the noise scale only by rho. So each participated app can configure their own row number, and based on it, we will calculate a global row number and finally get the noise scale. And for utility, we define the usage frequency level U as the invocation number of a certain query. And also we determine the accuracy level A via the % error formula. So A equals 100 times the absolute value of noise result minus actual result over actual result value. That means that the collaborating apps can set the required accuracy level after adding noise if the result of a query cannot meet the accuracy requirement set by the app, the query fails. And we also provide data contribution incentives. We have a global privacy level based on the contribution rate for each participating app. The more data an app contributes to a combined dataset, the higher the impact of the app on the overall global privacy level. This design prevents apps with only a small contribution but wants to get a lot of benefits from the combined dataset. Also, we have a bonus mechanism to reduce the noise scale. The more data an app contributes, the higher accuracy it can get. Finally, we have a noise increase scheme to further ensure privacy. Basically, the more questions an app asks, the more noise will be added. Finally, we use TE to protect the critical operations. The combined dataset and the operations like data management, queries, and differential privacy operations are executed inside the TE, so they cannot be compromised. Now let's look at our evaluation. Our evaluation will answer 3 questions. First, feasibility. Does GoBetween offer acceptable performance levels? And second, utility. Do GoBetween's data sharing collaborations satisfy dissimilar app requirements? And third, safety. How effectively does GoBetween eliminate the threats of apps uncovering their competitors' raw data? Here is our experimental setup. We built GoBetween by using Android open source project and OpenTE. We integrate our solution into Android's Java framework layer and native C and C++ libraries, and make the GoBetween as a system-level services in the Android system. This is our feasibility result. We evaluate the execution speed of GoBetween's critical operations. We can see that, in general, these operations take very short execution time. Even for the slowest one, storing 5,000 data into the combined dataset only needs about 48 milliseconds. To evaluate utility, we have a scenario. 3 apps collect geolocation data and collaborate via GoBetween to discover their users' favorite locations. And our user is Yeti, who, according to Nepal folklore, haunts the Himalayas. Specifically, App 1, App 2, and App 3 deposit with GoBetween 150 and 20 Yeti's locations, respectively. The experiment queries the combined dataset to determine the Yeti's favorite locations. Based on that, our query is how many times the Yeti visited a given area. You can see the result on this picture. The square, like area A, area C, area B, contains the number of the Yeti's visits to this area. And this number is each app's individual data collection without GoBetween and the combined dataset. For example, area A shows that App 1 records 17 visits of Yeti to this area, and App 2 45 visits, and App 3 0 visits. So the total number of visits is 62. That is the actual result of the query, how many times the Yeti visit the area A. And the bubble shape contains the query result for each app using GoBetween with the combined dataset. For example, this bubble shows that with the default settings for all requirements, after the query, App 1 got the result about 63, and App 2 got 66, and App 3 got 58. Remember, the actual query result is 62. That means, in that case, this privatized value still very helpful because it is very close to the actual value. And if all these apps increase their privacy requirement, then they will get these results. Kind of far from the actual value. So in that case, they got higher privacy and lower utility. There are also some other results. If you are interested, you can get more details in our paper. And basically, all these evaluation results show that GoBetween do balance privacy and utility with a good performance. Here is our safety result. The scenario is that an app M tries to reveal the actual value, so it executes a query. How many times does value 150 appear in the combined dataset? The actual value of this query is 20, so there are 20 records. If M contributes 20 records into the combined dataset. Its contribution rate is low, it's just about 16%. So after performing the query, M got the noised result, 11.26, which is far from the actual result. However, if M keeps depositing its data and its contribution rate got increased, then it can get the result that is very close to the actual result. That means that if M contributes a lot of data, it may reveal the dataset to some extent. So if M deposits a lot of fake data, then that will be an issue. One solution is to create a fake data detection module, and we will study it in the future. In conclusion, we provide an on-device framework, GoBetween, for differentially privatized sharing of sensor data. It is useful in dynamically adapting and balancing privacy and utility. It is incentivizing in rewarding active contributing app providers with higher utility. It is secure in protecting all shared data and relevant operations in TE. And that's it. Thank you for your attention. More details, please read our paper. Thank you so much.